We continue our investigation of the use of mixtures. We have seen that mixtures consist in taking building blocks, in our case the logit model, and to assemble them in order to make something more sophisticated. And we are looking at what kind of modeling objectives can we fulfill with these new tools. In the previous video, we started to investigate how to relax the IID assumptions associated with logit. IID stands for independent and identically distributed error terms. We saw in the last video how to relax the assumption that these error terms are independent across alternatives, and we obtained, using mixtures, a model which is basically similar to what we obtained with the nested logit model and the cross-nested logit model. In this video, we will investigate how to relax the other part of the assumption, the ID, the identical distribution. We have here a specification of a utility function where the error term are IID extreme value. Because we have included an alternative specific constant, we can assume that the location parameter is equal to 0. And because we are using a logit model and the error terms are IID, the scale parameter is the same for all alternatives, and actually for all individuals n as well. It is mu. As a consequence, the variance of this error term is the same for all alternatives, and it's given by the formula from the extreme value distribution. Now we would like to relax this assumption. Why do we want to do that? Well, let's take an example about familiarity. I'm a customer and I have the choice among many products, but some of these products I am familiar with because I have already purchased them in the past, I have used them, I know the quality and the imperfection. So I have a lot of information about these products. And there are other products on the market, new products, that I have never tried before. I'm not familiar with them. So therefore, it's kind of a strong assumption that the error terms, meaning the unobserved attributes, are the same for these two categories of products. And therefore, I would like to relax this assumption. I would like to relax the assumption that the error terms for familiar and unfamiliar products are the same. And in particular, I would like to allow the variance of these error terms to be different. I expect the variance to be larger for unfamiliar products, because there is more variation across the population, while for familiar products, it will be a smaller variance. This is my assumption from a behavioral point of view, and I need to be able to model it explicitly. We will use the same modeling trick that we did before. It's called including an error component. And that's what we have done in this equation. We have used the same specification as a basis, and we have included now a new error component that I denote sigma I psi I, and we assume that psi I has a normal distribution, and sigma I is the scale of this error component. And now we know how to deal with such models, right? We know the mechanism of a mixture of logits. We could calculate the choice probability conditional to psi, that would be a logit, and then we would integrate out the psi. So we know how to deal with it. So let's look at the error term now, the sum of these two components. So the error term, the epsilon, this is the error term of the utility function, is the sum of the error component that we have included, plus the IID extreme value error term that we had in the beginning. I have no clue about the distribution of this error term. It's the sum of an extreme value and a normal. I have no clue what kind of distribution it is. But I can calculate the variance, assuming that these two components are independent. In that case, the variance of the sum is the sum of the variance. So the variance of the first component is sigma I square, where sigma I is this scale parameter that I've included. And as we have seen previously, the variance associated with the IID extreme value terms is pi square divided by 6 mu square, where mu is the scale parameter of this nu. And now you can see that the variance of epsilon in that we just calculated depends on I. So it varies across alternative. So we will call this specification an alternative specific variance specification. As we discussed in the context of the previous video, there are identification issues associated with mixtures of logit. In the case of the alternative specific variance context, well, not all parameters, not all sigma parameters can be identified, and one of them must be constrained to 0. Unfortunately, contrary to what we do with alternative specific constants, it does matter which one we normalize to 0. We cannot choose arbitrarily. So I will not develop the theory about this, I will just give you the recipe what to do, and I refer you to the literature to understand where it comes from. So in theory, we need to normalize to 0 the smallest of the sigma. The problem is that we don't know which one is the smallest, right? So before estimating the parameters, we have no clue about the value. So the trick is the following. You first estimate a model which is overspecified, so that contains all the sigmas. Then you observe the estimated value, you identify the smallest one, and you constrain it to 0 before re-estimating all the parameters. So this is the solution which is proposed here. Okay, you estimate a model with a full set of sigmas, you see which one is the smallest, and you constrain it to 0. Let's show it on an example. So I'm using here the Swiss Metro example. Again, I have 3 alternatives. I have 2 constants, so I'm normalizing this one to 0. I have a generic cost variable, a generic frequency variable for the public transportation alternatives, and a generic travel time variable. And in addition to this specification, I will include the alternative specific variance error term that we have introduced in the previous slides. And I have estimated these models using the procedure that we know about mixtures of logits using Monte Carlo integration. And in this case, I have used 500 draws to generate these results. The table contains 3 models. The first model that I use as a reference is the logit model, where I have omitted the error term that captures the alternative specific variance. Then I have estimated, as I recommended in the previous slide, an alternative specific variance model with a full set of sigma parameters. And now we need to look at the results. And there is something strange about it. Is there anything that annoys you about these results? Well, remember, sigma is the scale parameter, right? This is the scale parameter associated with the error term that we have introduced. And one of them is negative. Okay, but usually we like to think about the scale parameter as the standard error, and a standard error cannot be negative. But this is not a standard error, it's just a parameter. So the interpretation of the parameter is that sigma is such that the square of sigma is the variance of this error component. And therefore, when you estimate these models, the sign is completely irrelevant, so just ignore it. And it is important because, as I mentioned before, you need to select the alternative with the smallest variance in order to be normalized. Therefore, in this case, the smallest variance is the one associated with car, because we have to omit the sign, we have to ignore the sign. And this is what I have done in the next column, is to re-estimate the model by normalizing the sigma car to 0 here. A couple of comments about the results. As we discussed already before, the parameters of the logit model and of the mixture of logit model cannot be directly compared. So you need to scale them before you compare them. And this is what we did in these columns. So we have divided each parameter by the cost coefficient. So this one becomes 1, and the other one have been calculated accordingly. Same thing here. We have normalized all the parameters by dividing by the cost coefficient. And you see that the fact that you account for this alternative specific variance has a significant impact on the parameters. Okay, so this is important to take this into account. And there is another sign, is that the likelihood, the final log likelihood, has improved a lot, which is a sign that this term contributes a lot to explain the behavior. Okay, so let's talk about behavior. So remember, my motivation to include this error term is to look at the familiarity, to say that, okay, people may be familiar to some alternatives and may be unfamiliar to other alternatives. In this case, I'm talking about a stated preference data where I have one alternative which is called Swiss Metro, which is an hypothetical high-speed train that probably will never exist. And in any case, respondents never experience this mode of transportation, while the respondents are familiar with traveling by car and traveling by train. So we have a very good example here of a case where the level of familiarity from each respondent is different across alternatives. And this is reflected in the results. So if you look at the variance of the Swiss Metro, this is the largest of the three, which is consistent with my interpretation, because people don't know, they are more uncertain about this alternative. And the fact that we took this into account improved a lot the fit and affected significantly the parameters. So this may be an important feature to include in a model. Mixtures of logit can be used to relax the assumption of identical distribution among error terms of different alternatives. In particular, a model with alternative-specific variance parameters can be specified. Again, identification issues are not straightforward. In this case, we have seen that one of the parameters has to be normalized to 0, but it is not arbitrary which one we have to choose.